We're going to do this video in a little bit more of an abridged version. If you have your slide sets, then you can kind of follow along. We'll pull over to another kind of blackboard and add some things here and there, but you should be able to just follow along with things for the most part. So this section is about chemistry, and chemistry is a topic that I will gladly admit has terrified me at certain times in my education. I was not always a very good chemist, and over the years I actually became a good enough chemist that I started tutoring it and finally teaching it until biology just took over more of my time than chemistry did. And I still kind of like teaching chemistry because I know it's something that intimidates a lot of people, and they just don't feel like they can put their hands on it and really dig into it. But it's got a really interesting quality to it, and if you understand it, you can make some connections to other things that you maybe can't make otherwise. So chemistry is the study of matter, all the stuff that makes up everything that's all around us. And we talk about matter, we very often talk about solids, liquids, and gases, that these are the forms that matter comes in. And so if you start thinking about, well, if matter's everything that's solid, liquid, and gas, what does that leave behind? You know, what's not a solid, liquid, or gas? Because if you just look around your room, everything falls into one of those categories. Well, almost everything falls into one of those categories. And so I guess that's something I would make a little note about, is as important as knowing what matter is knowing what's not matter. And not matter would be forms of energy for the most part, if you think about it. So things like heat and light. And our understanding of energies like heat and light continue to grow. And so sometimes we talk about it actually as if it's a form of matter, and sometimes we talk about it as if it is not, because it has characteristics that sometimes seem to fall in and sometimes don't. But either way, these would be typically things we would qualify as not being matter. When we talk about matter, we typically speak in terms of elements and atoms. So elements are the types of matter that we have, or the flavors of matter is one way that I have sometimes put it. And then atoms are how we count matter. It's the units that we talk about. Sometimes we use the term molecules, but this is really just a variation on the concept of atoms. There are 6 really major elements that we talk about in biology. Their names and symbols are relatively simple and should be somewhat familiar to you. And in terms of the weight of living things, these make up most of what living things are. And it's because they're in the molecules and compounds that are the building blocks of living things. So carbon with the symbol C is found in all living things. And I want to clarify that just a little bit. What do I mean by it's found in all living things? Well, I mean that it's in our building blocks. So there are 4 major building blocks of living things, and we refer to them as macromolecules. And if you look on the side of any box of food, you will be able to find these pretty easily, because we also know these building blocks as nutrients. So they are carbohydrates, including sugars and fiber and all of those things. Lipids, or what we would most commonly know as fats. Not all lipids are fats, but all lipids are fat-like, and that's what binds that group together. Proteins, an important nutrient, and then nucleic acids. And nucleic acids are things like DNA and ATP. And you may not think of those as nutrients, but very certainly I hope you think of them as building blocks of living things. So carbon is significant because it actually forms the skeleton or the backbone of all 4 of these types of molecules that make up our bodies. Hydrogen is also found in all of those molecules, as well as in good old H2O, water. Nitrogen is specifically found in proteins and nucleic acids. Oxygen is found in all of those macromolecules along with water. And then phosphorus is a significant player in living things because it's in our DNA and our ATP. And in addition to that, it's even in some lipids. I'm just going to squeeze that in here. Sulfur plays a big role in our proteins. I'm going to scratch this out. I would actually not like to talk about sulfur in DNA. Really just in our proteins. And it's a very small job, but it's a very important job, as we'll find out a little bit down the line here. So those ones are significant because they physically make up the chemicals that make us up. Then there's other elements that are really important to us because they do very important jobs in our bodies. Sodium's one of them. Notice that it has kind of an odd symbol because, of course, S was already taken up by sulfur, and so they had to come up with another symbol. So they went to the Latin name for this element, which is natrium, and used the symbol Na, taken from that name. This is significant in our muscle and nerve cells. It's also useful in our bodies for water balance, so that's kind of a side note maybe. Calcium is, again, a big part of how our muscles contract and how our nerves make electricity. It is also important to bones, and that's where most of us think of it as being useful. And then I want to add one more here. It has a big role in enzymes and how enzymes work. If you haven't watched the enzyme video yet, what you'll find out is that enzymes accelerate chemical reactions. Chemistry is naturally a very slow process. And so in order for chemistry to happen at the speed of life, where you're getting energy from the breakfast you ate within a few minutes to a couple of hours, we need to speed up the natural tendencies of chemistry. Chemistry is actually a very tricky thing. You have to be in the right position, you have to be moving at the right speed, and you have to actually run one chemical into the other chemical under those conditions, which means that successful chemical reactions don't take place very often. And that's why chemistry is typically thought of as being a relatively slow process. Most of the chemical reactions that we might think of, like using yeast to bake bread, or maybe making a baking soda and vinegar volcano, work very quickly because we've provided a very concentrated amount of chemicals, and so that helps speed up the reaction. But even in our bodies, chemicals are not typically highly concentrated. In fact, all of the chemicals that are dissolved in our bloodstream make up only 2% of our blood. So they're very dilute. And the chances that they run into each other at just the right time, in just the right position, at just the right energy level, is pretty slow. And so enzymes play a major role because they help those things happen. The right place, the right time, the right energy. And so they speed things up to the speed of life. Potassium is critical to muscle and nerve cells as well, and also involved in some water balance action. And then we have some kind of less common ones. Magnesium, also a player in enzyme reactions. Chlorine, again used by our muscle and nerve cells and in water balance. And then iron, which of course most of us are aware that our red blood cells use to carry oxygen. When we talk about atoms, we very often talk about molecules, which is a group of more than one atom, and compounds, which is a group with more than one element. And if you think about this for just a minute, if a compound always has more than one element, then all compounds will automatically be molecules. It won't happen very often that you'll have to read chemical formulas, but they do sometimes pop up in your text, and they do sometimes pop up when you're doing internet research. So I wanted to make sure you knew roughly how to read one. I don't need you to memorize the names of any chemicals. I just want you to have a basic foundation of how chemical formulas are developed and how you can read them. So every symbol you'll notice starts with a capital letter, which means every time you see a capital letter, you're moving on to the name of a new element. And some of them will have little numbers below them. And if you see those little numbers below, those subscripts, that tells you how many of that atom there is. Obviously, if there's not a subscript, then we probably just have one. So if you just saw the letter H, that would tell us we had one atom of hydrogen. If you saw an O2, it's 2 atoms of oxygen. If you see H2O, it's 3 atoms. 2 hydrogens, and 1 oxygen. Some of the more complex ones, like K2SO4, its formal name is potassium sulfate. That's not something you're responsible for in a class like this, and on the rare occasion when I need you to know the name of a complex molecule, I'll make that clear. But what I'd like you to be able to do with that at this point is tell me that there are 3 elements there, potassium, sulfur, and oxygen, and that there are 2 atoms of the potassium, 1 atom of the sulfur, and 4 atoms of the oxygen, so a total of 7. It's only about 1 question like that on the test, so it's not like you need to spend hours and hours getting that figured out, but just a basic idea of how those symbols, what those symbols represent.